Today, I'd like to start off by acknowledging the First Nations, the Inuit, and the Métis people of the place we now call Canada. It has been my privilege to live, work, travel, and learn on the traditional territories and ancestral lands of our Indigenous peoples. I currently call Calgary home, which is the traditional territories of the people of Treaty 7 region in southern Alberta. The city of Calgary is also home to the Métis Nation of Alberta, regions 5 and 6. At the University of Calgary, we have an Indigenous strategy. It's called a Tapato, and it was developed with this philosophy of walking parallel paths together in a good way. It's a phrase that resonates with me, and I sat with it a bit, and 3 themes kind of came to mind that are really important to me and to the work that I do. These are: first, go with, not against nature. 2, to expand our community and redefine what together means. And 3, to engineer in a good way. They're my parallel paths. So today, really what I want to do is hone in on this theme of working with, not against nature, and how engineering in a good way has changed. So let's explore the permafrost. It's cold up here in Canada. What's up with the thawing? Why do we care? How might we approach this predicament? Let's take a walk together with nature. Permafrost is defined as ground that remains at or below 0 degrees for 2 or more consecutive years. This is important because permafrost defines a thermal state of the ground. It could be soil, rock, peat. It might contain ice or it might not. So that's the reason when we talk about permafrost, we say it thaws, it doesn't melt. Engineering on permafrost ranges from mining with mine design, frozen core dams, things like all sorts of tailing facilities, seasonal roads, all-season roads, ice roads, pipelines, railroads, homes, and community infrastructure. And over the last 50 years, geotechnical engineers have played a starring role in what happens in terms of cold regions engineering. We've got innovations in consulting to research, but our main design premise has always been keep it frozen. What keep it frozen means in practice is that design is governed by thermal conditions. And that differs significantly to how we engineer in the South, where we may rely on things like bearing capacity or settlements, like an ultimate or a limit states design. As permafrost engineers, we look to the frozen ground properties. So we look at high strength, low permeability, increased stiffness, and we use the properties of the ground. So just to give you an example of what this looks like, if you're going to build a road, the road embankment in a permafrost region would be designed to have sufficient fill to bring the level of the permafrost up to the base of the embankment. And what that does is it protects the active layer, the top layer, as well as the permafrost layer. So we're not building for strength, we're building it up to protect the thermal condition of the ground. There's scenarios where that thermal regime is more challenging, and we have ways of addressing that with the use of thermal siphons, like you can see in the photograph here, or insulating layers, high albedo surfaces, all of which are still working towards this premise of keep it frozen. So despite this apparently simple message, let's just keep it frozen, we of course have had some spectacular failures due to thaw. So here's just one example. This is a road just east of Yellowknife, and it was built on ice-rich permafrost. And what happened is vegetation was removed, road was paved over, and that changes the thermal regime of the ground. You can see that because of the ice richness, there was some settlement. I'd call this differential settlement. And so what happens when we start to disturb the ground state is this is the result of it. So it took us a little while, but we learned really to minimize any disturbance to the permafrost. We tried to figure out how to engineer with nature, how to keep that thermal regime in place. So simple techniques would be, for example, like winter construction, thermal embankments. Okay, so everything's great. What's our predicament? Well, understanding the thermal response of permafrost has been critical in the development of innovating engineering solutions across the north. I mean, we have things like frozen core dams. Like, how cool is a frozen core dam, right? But what about now? Well, in the face of climate change and complexities, the likes of which we have not seen before, we've got climate warming scenarios that surpass our predictions. We've got changes in precipitation patterns. We have extreme temperatures. We have Arctic amplification. How are current climate forecasts impacting the thermal stability of the permafrost? And so that starts to beg the question, can we still keep it frozen? And so hence we find ourselves in a little bit of a permafrost predicament. I like alliterations, if you can't tell. They make me a little bit happy. So let's take a look at two examples. So the first example where climate adds complexity is the coastal erosion of Tuktoyak Island. Tuk is an Inuvialuit hamlet just shy of 1,000 people. It's located on the shores of the Arctic Ocean at the tip of the Northwest Territories in northern Canada. And it has this island, you can see in the picture here, that shelters the community from the full impact of the Arctic Ocean. It's a natural wave break for the island, for the community, sorry. But the island is disappearing, and it's disappearing fast. Erosion rates are up to 2 meters per year. These unprecedented rates of coastal erosion on both Tuk Island and on permafrost bluffs across the Arctic are driven by some complex intertwined thermal and mechanical processes. But in the driving seat of all of that is climate change. How does climate accelerate erosion? It's things like warmer and longer summers. It's a decrease in the sea ice. It's a relative sea level rise. It's extreme storm surges. That's actually a really important one. It's warmer ocean temperatures. So many homes in Tuk have already been relocated despite numerous remediation measures. So here's a case where keep it frozen is just not going to work against the climate forces that we're seeing today. The second case I'm going to touch on to illustrate the complexities of climate change is the Hudson's Bay Railway. The HBR travels from the Paw to the Port of Churchill in northern Manitoba. And along its path, the rail spans from areas of no permafrost to sporadic to discontinuous to continuous permafrost zones as it heads north. The track travels over widespread ice wedge polygons and some frost-sensitive glacial marine deposits. In 2017, extensive flooding caused rail disruptions for 18 months, and the Port of Churchill, which is one of Canada's few deepwater ports, became fly-in only. HBR was designed for stable, equilibrium permafrost conditions, but it's now facing significant climate-driven stability and drainage problems. These include challenges such as floods, washouts, surface subsidence and settlements, sinkhole formations, infrastructure damage. So the climate complexities the HBR face are in how to understand and work with nature. And this is part because the southern parts of the rail are under imminent climate threat, whereas the northern portions have more time. So what sort of design and mitigation measures should be considered? Will keeping it frozen stop working at some point? But in an environment where water management is such an issue, will thaw be a potential solution? It's just something to start thinking about. How will we make this all work? So this vulnerability of permafrost to climate change depends on complex interactions between numerous factors. It's like topography, it's water, it's vegetation, it's snow. How do we address these complexities? How do we start thinking about engineering in a good way? Well, there's a couple things we might really want to consider. One is that climate change is more than just temperature warming. It's extremes. It's rainfall earlier and later in the season. It's changes in snowfall patterns. It's change. How does that change translate to geotechnical models? Certainly it's more than a warming number every year. The second is understanding uncertainty, risk, and reliability. Really helps put things into perspective. It makes use of data in a way that can both be communicated and understood. And the third is really understanding scale. So setting up engineering frameworks, risks maps, helps us understand and clarify the scale at which we are working. And that helps us translate processes into usable methodologies. It creates structure so that continuous updating, improving, and adapting can be performed in systematic ways. Those are all good, but maybe what we really need to do is go back to what I said at the beginning and say, well, how can we listen to the land? What is nature telling us? It very well may be that nature is telling us something new and different. Maybe there's a new paradigm that is emerging. In some areas, it might no longer make sense to keep it frozen. Maybe now we need to look at how do we thaw it. So over the next number of years, my group, as well as I know others for sure, are looking at how we can model things like controlled thaw. Should we speed it up? What happens when we induce thaw too soon and it could freeze back? There's so many interesting engineering challenges ahead of us as we work in the north. And as we look towards the future, our engineering solutions for the north need to carefully consider the project, its lifespan, the anticipated climatic conditions, including extremes and other changes over the project lifespan, and come up with a solution that works with nature and not against it. And understand that nature is different now than it was 40 years ago, than it was 20 years ago. So how do we stop fighting nature? Well, that's where the great news comes in. As geotechnical engineers, we know how to do this. Adaptive design solutions that allow for future adjustments. Sounds like something I learned about. That's the observational method. So maybe walking a parallel path with nature in a good way is observe, adjust, integrate, and adapt. Maybe it is the observational method. Thank you.